This is your presenter Asloob Mudassar, and I am presenting slide number 10 of the course on laser physics. The question is, calculate the net gain in one round trip through a laser cavity during the lasing process. The answer is, during the lasing process, photon amplification occurs through the active medium, and losses occur at the reflectors of the resonator and in the space between the two reflectors. The major losses may include non-radiative decay and spontaneous emission decay and others. Let Li represents the total loss in the cavity region between the two reflectors during one pass, and let capital F is the photon flux in the laser cavity just after the reflector 1. Through the active medium, the gain in the flux, which is dF, is given by equation 7.2, which is reproduced in equation number 10.1 below. So dF over F is equal to sigma 2, and within parenthesis we have N2 minus G2 over G1 times N1, and then this parenthesis is multiplied by dz, where N1 and N2 are the number of particles of the active medium in level 1 and level 2 respectively, and G1 and G2 are the degeneracies of level 1 and level 2 respectively, and that the population inversion exists in the cavity for which N2 is greater than G2 over G1 multiplied by N1. So it means that equation 10.1 corresponds to the process when the lasing action has started, and that is the population inversion has been achieved. The stimulated emission cross section is sigma 2,1. If L is the length of the active medium, then the integration of equation 10.1 gives. So we are integrating both sides of this equation, which you can see over here. And on the right hand side we have the limit from 0 to L, because L is the total length of the active medium. And then you know that all these quantities except dz will remain within the integral. The rest of the quantities being a constant will be taken out of the integral. And so on the right hand side we have replaced the integration of dz with L plus some constant. And on the left hand side we have the log of f, the integral of df over f is log of capital F. And you know that simplifying this equation, we can write that f prime is equal to f into e to the power sigma 2,1, and within the parenthesis we have N2 minus G2 over G1 multiplied by N1 and then multiplied by L. So this is equation 10.2. So you see that this gives the flux as a function of the distance L through the laser cavity or through the active medium. So f prime is the gain in photon flux in one pass of the cavity. The loss in one pass of the cavity will be f prime into Li, because here we have said that Li is actually the total represents the total loss in the cavity during one pass. So that's why we have written down this loss term over here. That is, the loss in the pass in one pass of the cavity will be f prime into Li, because f prime, you know, that is the flux that we have calculated, or that is the gain in the photon flux in one pass multiplied by the loss term, which is Li. Thus the net gain in one pass of the crystal in one pass of the cavity is f prime minus f prime L. So we have subtracted the gain from and we have subtracted the loss from the gain. So the left hand side will give you the net gain, that is f prime minus f prime into Li is the net gain, which we have written on the right hand side by taking f prime as common. So f prime is equal, so that is equal to f prime into 1 minus Li. So actually this is the net gain in one pass of the cavity. This is the photon flux which is incident on the reflector too. So you see that this net gain, which we have written as f prime into 1 minus Li, is actually the net gain which was achieved when the flux traveled when the flux traveled from the reflector R1 and to the reflector R2. So this is the photon flux which is incident on the reflector 2. Let R2 is the power reflectivity of the reflector 2. Then the net gain in the flux starting from the location within the cavity just after the reflector 1 and ending at the location just after the reflection from the reflector R2 is. So you see that now we have written down we have included the reflectivity R2. Here we have defined that R2 is the power reflectivity of the reflector 2. So you see that when this field, which we have written f prime minus f prime into Li, is incident on the second mirror, the power reflectivity will be multiplied. So we have multiplied on both sides by R2. On the left hand side we have multiplied by R2, and on the right hand side we have substituted the value of f prime. That is, f prime has been replaced by the right hand side of equation 10.2. So this is, you see that this is the flux. This flux will travel back towards the reflector R1. So after reflecting from the reflector number 2, this will propagate backwards towards the reflector R1. So this flux will travel back towards the reflector 1, and thus the net gain in one pass, in one round trip, that is just after the reflection from the reflector R1 is. So you see that we have written the two terms. The first curly bracket on the left hand side indicates the contribution from one pass when the flux traveled from after the reflector R1 and then bounced back from the reflector R2. And then on the right hand side the curly bracket gives you the contribution when the net flux traveled from R2 towards R1, and this is the term which corresponds to the power reflectivity by the mirror R1 or by the reflector R1. So you see that if you multiply these two terms, then you know that it becomes the contribution of the flux in one pass, and the second term gives you the flux from the second pass. So this total becomes the flux in one round trip. And this is equal to the right hand side, or the last term on the equation 10.3 is f into R1 into R2. Within the bracket we have a minus 1 minus L1 whole square, and into e to the power 2 sigma 2 1 into within bracket we have N2 minus G2 over G1 into N1 into L. So this is the net gain in a laser cavity in one round trip. So you see that this is what we wanted to calculate, because you see that we have also included. Notice that in these curly brackets we have 1 minus Li, which is actually the loss term. So we have, and the other terms are actually the gain terms. And R2, you see that R2 and R1 are the power reflectivities of the reflector 2 and the reflector 1. So you see that we have included all these one, and FUC is the total flux which was initiated, or which was the flux just after the mirror, just after the reflector R1. So we started just after the reflector R1, then we completed one round trip just after R2, and then from R2 to we traveled back, the flux was traveled back towards the reflector R1, and the second term is the contribution after the reflector R1. So the net contribution in one round trip has been given in the last step of equation 10.3. So this is the net gain in a laser cavity in one round trip. And you know that this is the end of slide number 10.